In behavioral psychology, learning is defined as a relatively permanent change in behavior resulting from experience. Classical conditioning is how an organism learns to associate stimuli. It allows a neutral event to take on the biological power of a reflexive trigger. These mechanics were first documented in the early 20th century through the physiological research of Ivan Pavlov. Pavlov's work is frequently categorized as a simple, passive pairing of two events happening at the same time. This process involves the brain actively mapping the relationship between different signals to build an internal model of its environment. To understand the logic behind human and animal behavior, we must map the specific life cycle of an association. This reveals a system that follows a rigorous internal architecture. This architecture was first isolated in controlled laboratory environments, where the individual variables of learning could be separated. We begin with the unconditioned stimulus, or UCS. This trigger, like food or an electric shock, elicits a biological response without prior training. The resulting physiological reaction, such as salivation or an automatic fear response, is the unconditioned response. This is a hardwired reflex. A conditioned stimulus is a neutral event, like a tone, that gains influence only after it is repeatedly paired with the unconditioned stimulus. Once the association is formed, the subject produces a conditioned response, a learned, anticipatory reaction to that specific signal. While the biological reflex and the learned response may look identical in practice, they are driven by different internal mechanisms. A neutral event only becomes a conditioned stimulus when it successfully links into an existing biological pathway. Traditional models often emphasize contiguity, the idea that learning occurs simply because two things happen close together in time. However, conditioning is more accurately described as a calculation of contingency. It depends on whether one event reliably predicts the arrival of another. This is evident in simultaneous conditioning. Here, the signal and the biological trigger turn on and off at the exact same time. Because the signal provides no advance warning, it offers no informational value. The brain ignores it, and conditioning fails to take place. The most effective method is short delay conditioning. The signal begins first and remains present until the biological event starts. This arrangement works because the stimulus functions as a clear warning signal. It provides the data the organism needs to anticipate what follows. If the signal ends before the trigger begins, we have trace conditioning. This requires the brain to maintain a memory of the signal across the empty time gap. These patterns show that the brain is not just recording coincidences, it is analyzing temporal sequences to build predictive models. Once an association is established, it follows a measurable and predictable life cycle. During the acquisition phase, the strength of the learned response climbs rapidly before reaching a stable plateau. If the signal is repeatedly presented without the biological reward, the response declines. This is the process of extinction. Extinction does not mean the brain has erased the original memory or unlearned the connection. Instead, the brain learns a new inhibitory rule, a secondary association that the signal no longer predicts the trigger. This new rule suppresses the old one. This is proven by spontaneous recovery. After a rest period, the conditioned response can suddenly reappear even without any new training. The sudden reappearance indicates that the original neural connection remained intact. It was simply being actively held back by the brain. Organisms must also manage stimulus generalization, reacting to similar signals, and discrimination, the ability to differentiate between a predictive signal and an irrelevant one. The life cycle of an association reveals the brain as a dynamic processor, constantly balancing excitatory and inhibitory rules based on incoming data. By the mid-1960s, researchers began looking past outward behavior to understand the cognitive processing that makes learning possible. In 1968, Leon Kamen identified a specific boundary on how and when the brain forms new associations, known as the blocking effect. In the first phase of Kamen's experiment, an animal learns that a light predicts a mild shock. In phase 2, a second signal, a tone, is added. Both the light and the tone are presented together and followed by the shock. When the tone is later presented by itself, the animal shows no reaction. It has failed to associate the tone with the shock. This occurs because the light already fully accounts for the shock. The tone provides no new information. This confirms conditioning is not a passive result of pairing. If a signal lacks predictive utility, the brain does not incorporate it into the model. Classical conditioning is a sophisticated system for processing environmental data. It functions according to specific requirements. It depends on temporal contingency, moves through a life cycle of inhibition, and requires the presence of new information. This associative structure allows an organism to anticipate biological events before they occur, using the past to navigate the probability of the future.